In this video, we break down the 5 key features of a balanced chemical equation using the simple mnemonic SCARP that allows you to understand, build, analyze, and check balanced chemical equations. And we're going to use the same equation throughout the entire video for simplicity and consistency's sake. So S stands for smallest whole number coefficients. Coefficients are the numbers in front of each molecule, and it tells you how many of each are present in the balanced chemical equation. Likewise, which of these 3 is the correctly balanced equation for the creation of water? Top, middle, or bottom? That's very much analogous to asking which of these 3 fractions is the simplest, most reduced form. Technically, they're all equivalent, but because there's an infinite number of fractions that equal 0.5, we want to choose the one with the simplest, smallest numbers possible as a single representative of that 0.5 value. That's why we would look at 8 H2s reacting with 4 O2s, making 8 water molecules, as nonetheless 2, 1, and 2 for the coefficients, because that's the smallest whole number coefficients possible. Visually speaking, this is what the smallest coefficient situation looks like, where we have the minimum number of molecules possible to make this reaction occur. 2 molecules of H2, 1 molecule of O2, and 2 water molecules. This is also what's called a single unit of reaction, and the rest of this video will show you exactly what that means and help you avoid common misconceptions and pitfalls. C. A balanced chemical equation follows the law of conservation, which states that certain quantities, mainly matter, mass, and energy, cannot be created nor destroyed, and instead are transformed and or rearranged. Most obviously, a balanced chemical equation illustrates conservation of atoms. There are 6 atoms on either side of the equation. We start with 6 joined together in certain combinations of molecules, then they undergo the reaction, and they break apart and rearrange into new combinations of molecules. It also follows the law of conservation of mass, such that the sum of the mass of all the products equals the mass of all the reactants. In case you're wondering, AMU stands for atomic mass units. But what about the law of conservation of energy? Does that apply to all balanced chemical equations? Here, the total amount of energy of all the reactants and that of the products is clearly not the same. However, we nonetheless must make up for the difference. What we see here is an exothermic reaction, where a higher energy set of reactants turns into a lower energy set of products, with the deficit released as heat. Therefore, we can say that a balanced chemical equation, and thus the chemical change it represents, abides by the law of conservation of atoms, mass, and energy. A stands for atoms match each other. I mentioned earlier that atoms are the most obviously conserved quantity in chemical reactions. So technically this is an extension of the previous point, but it's also meant to dispel misconceptions, connect everything together, and understand exactly what a single unit of reaction is. Here's a super confusing question. How many hydrogen atoms are in a single unit of reaction? 4 or 8 hydrogens? Believe it or not, there are a total of 4 hydrogen atoms present in this reaction, even though there are 8 green hydrogen circles that we see. But that's the essence of conserving something from beginning to end through a process. It's sort of like saying, I see 2 pictures of myself. One when I was 10, one when I was 15. Yes, we see 2 of me, but I'm just one person, and my existence was conserved through the process of aging. Similarly, in chemical reactions, atoms don't vanish, they just simply get reattached. For example, this hydrogen started out as part of H2, and now it's a part of a water molecule. That's why atoms match each other. And in this case, 4 H's and 2 O's are on both sides of the equation. This must be the case for achieving a correctly balanced chemical equation and to ensure we follow the law of conservation. Whether we have 1 or 100 reactions, the law of conservation means that the atoms must match. 24, 24, 12, 12. Here, we fail that test because hydrogen atoms don't match. All it takes is just one of the atoms to not match and we fail the law of conservation, which can't happen because we have to abide by the law of conservation. Let's talk about ratios. It's different for atoms versus molecules. It's super important to recognize that for this reaction, we have a ratio of 4 to 2 hydrogen to oxygen atoms. Even as the reaction scales up here to 16 and 8 atoms respectively, the 4 to 2 ratio is retained. But hold on a second, shouldn't we reduce that ratio from 4 to 2 to 2 to 1? Didn't we say we want to have the smallest whole numbers? This is the most commonly misunderstood thing about chemical reactions. It's not that the atoms must be in the smallest whole number ratios, it's that the molecules must, the coefficients must. Ultimately, this is because you can't have a fraction of a molecule. You can't split an O2 molecule in half and have it be the same molecule. So this right here is no longer the chemical reaction of interest. Even if 3H2 plus 1.5 O2 plus 3H2O matches atom counts, it follows the law of conservation, it's not chemically valid because, again, molecules aren't divisible. You can't chop them in half. That's why we have to rewrite the equation to use the smallest whole number of molecules. And that's often a scale down, 3 down to 2, 1.5 down to 1, 3 down to 2. Please pause the video and write this down. Lastly, chemical equations are scaled proportionally in a very specific way. Key question: how many units of reaction do we see here? 2, 3, or 4 units of reaction? Remember, unit of reaction is the smallest number of whole molecules that can react together. In this case, it means that we have 2 H2 molecules reacting with 1 O2 molecule to form 2 water molecules. It also includes 4 total hydrogens and 2 oxygen atoms on both sides, all conserved, just rearranged. Here's that same single unit of reaction highlighted, and there's simply 4 times that, so 4 units is the correct answer. In comparison to a single unit of reaction, 4 units have 4 times the oxygen atoms, 4 times the hydrogen atoms, 4 times the atoms in general. 1 unit has 6 atoms, 4 units have 24, 4 times the H2 molecules, 4 times the O2 molecules, 4 times the water molecules, and 4 times the molecules in general. 5, 20. Thus, we can say that both the atoms and the molecules scale proportionally. Whether it's 2 units, 4 units, or even 10 units of reaction, or a million units of reaction, the atoms of each element remain balanced on both sides. Conservation, therefore, always works no matter how many units of reaction we scale it by. But as we've established, there's only one set of coefficients, the smallest whole numbers possible, that constitute our correctly balanced equation, our single unit of reaction. Therefore, we can say that satisfying the law of conservation is necessary, but not sufficient. It's not enough to properly balance the chemical equation. Even for situations like we saw earlier that don't work because we have partial molecules, we may still pass this matching atom test, 6 and 6, 3 and 3, even though it's not correctly balanced. If we go back to this slide, everything is simply scaled from one unit of reaction: the number of each molecule, the coefficients, and the number of each atom, respectively. However, just as we can't have a fraction of a molecule, we can't have a fraction of a unit of reaction. We can't have 1.5 units of reaction or 2.5, so we must have a whole number worth of units of reaction. And that's very interesting because it creates an alternation of acceptable and unacceptable combinations of atom counts. 4 and 2 works, 6 and 3 doesn't work, 8 and 4 works, 10 and 5 doesn't work. For this reaction in particular, the pattern would be not only that H is twice as much as O, but everything is a scale of 4 and 2, such that both the numbers have to be even numbers. So if we look at all of the unacceptable, the red boxes, oxygen counts are odd, which can't happen because that would correspond to a fraction of a unit of reaction. And as I've established, we can't do that because we can't have a fraction of a molecule. We can't reduce the atom ratio from 4 to 2 down to 2 to 1. Here's a great check for understanding. How many hydrogens and oxygens, respectively, do we have with 100 units of reaction? Very simply, we take the 4 hydrogens and 2 oxygens from 1 unit of reaction, and we scale it, we multiply it by 100. So that gives us 400 and 200 respectively, because 100 times 4 is 400, 100 times 2 is 200. Let's flip the scenario. How many units of reaction involve 150 hydrogens and 75 oxygens? Well, it's actually not going to be any of these because it would correspond to a fractional number of units of reaction. Remember how I said earlier that we cannot have an odd number of oxygen atoms. The only acceptable atom counts are where both the hydrogen and the oxygen have an even number of them. I highly recommend that you write this down, take a screenshot, because it will help you navigate chemical equation problems and see connections. Also, give this video another watch to sink in, comment your questions, and please have a great day.